This is lecture 11B for Calculus 2 on the monotonic convergence theorem for sequences. In the second new theorem, it concerns what are called bonded monotonic sequences, and it says that every bonded monotonically increasing or monotonically decreasing sequence converges. To really understand what this theorem is, we have to develop quite a bit of vocabulary, and in doing that, we start developing the vocabulary of mathematical analysis. I think that the book was a little cavalier in how they presented these definitions, so I'm going to try to be a little more precise. In mathematics, the words increasing, decreasing, and monotonically are generally not used alone. The words increasing and decreasing should be used with the qualifier strictly, if that's the case. Strictly increasing means, for sequences, that the next term is strictly greater than the previous term. Strictly decreasing, of course, means that the next term is strictly less than the preceding term. If this isn't the case, you can use the word monotonically. So these are increasing or decreasing sequences. One, in which case you just simply have the greater than or less than sign, is associated with the word strictly. Now, in case the next term is greater than or equal to the previous term, or less than or equal to the previous term, all in red, then the word monotonically precedes increasing or decreasing. You say these are monotonically increasing or monotonically decreasing sequences. On the other hand, you can use the word non-decreasing and non-increasing. You see that here. If it's monotonically increasing, then it is non-decreasing. Right? You can use either one of those terms. Now, I do accept the word monotonic to mean either monotonically increasing or monotonically decreasing. In other words, it's increasing but could have a little plateau in it where the terms are the same for a while. That's what this means. The sequence is bounded from above if there exists some real number, which I'm going to call capital M, right, such that all the terms are less than or equal to this real number M for all n. Then M is called an upper bound. Note that there can be an infinite number of upper bounds. For example, if the sequence is less than 100, all the terms of the sequence are less than 100, they are also less than 200. They're also less than 1,000. So what we look for, once we find that it is bounded from above, we want to find what's called the least upper bound, the smallest of these upper bounds. If all the terms are less than 100, I really don't care. They're also less than 200 or 1,000. You know, I want to find the least number, the least value of M, such that all the terms are less than or equal to this M. By what's called the completeness theorem of real numbers, says that if a non-empty set of real numbers, and a sequence is a set, if a non-empty set of real numbers has an upper bound, then it has a least upper bound. So we know that exists. The completeness axiom of real numbers just says there's no holes in the real numbers. Okay. So the least upper bound is the smallest real number M, such that all the terms are less than or equal to M for all n. You can also call this least upper bound the supremum and abbreviate it SUP for short. And least upper bound you can abbreviate as LUB, and you'll see that in the literature. So again, what we're saying is that there is a bound. The sequence is bounded from above. Fine. Is there a least upper bound? By the completeness axiom of real numbers, there is a least upper bound. And we call that least upper bound the supremum, SUP, or the least upper bound, LUB. And we can look in the other direction. Is the sequence bounded from below? Let's say that there is a number M, little m, such that all the terms of the sequence are greater than or equal to this little m. Then M is a lower bound. Again, by the completeness theorem of real numbers, if a non-empty set of real numbers, which this sequence is, has a lower bound, then it has a greatest lower bound. Right. That means there is a largest real number M, little m, such that M is less than or equal to a to the n for all n. This least upper bound is called the infimum, inf for short, or you can sometimes just see greatest lower bound, abbreviated GLB. A bounded sequence is one that's bounded from both from above and from below. And now we can state that new theorem more precisely. If a sequence is monotonically increasing, that is, it is a non-decreasing sequence, and is bounded from above, then by the completeness axiom of real numbers, it has a least upper bound. This sequence converges, and it converges to its least upper bound. Similarly, if the sequence is monotonically decreasing and it's bounded from below, then by the completeness axiom, it has a greatest lower bound. In addition, the sequence converges, and it converges to its greatest lower bound. And here is a picture. You can see just exactly what it is. Here, the red dots are the values of the sequence, and they are, as you can see, sort of assume that it's, what's being shown here is that it's non-decreasing. I have no idea what this little glitch here is, but let's get that glitch. All right, say it's a non-decreasing sequence. They're always increasing, and yet they still always stay less than the line that's highlighted in blue. Right, and if they're always less than the line highlighted in blue, and the line highlighted in blue is their least upper bound, this sequence will converge to the least upper bound. Here's a proof. Let's let L be the least upper bound. It's the least upper bound of this monotonically increasing sequence a to the n. The statement concerning least upper bound means that for any epsilon greater than 0, there's a number L minus epsilon that is not a least upper bound because L was the least upper bound. So if you move any lower than L, you don't have an upper bound. This is the L I'm talking about. I'm sorry, the font changes, but I mean the same font here. Okay, same number L. Because this is not a least upper bound, there is some number n such that the terms of the sequence are greater than it. In other words, you've kind of trapped the sequences now between L and L minus epsilon. So rearrange this, rearrange the statement here, and get the statement: the absolute value of L minus a to the n is less than epsilon for all n greater than capital N. This is a precise definition of the limit of a sequence. Hence, the sequence converges to L, its least upper bound. The criteria for Theorem 2 can be relaxed by saying if the sequence is eventually non-decreasing or eventually increasing. And that means the first couple terms of the sequence are forgiven, such as, say, we're not going to look at your grades for the first 2 years. We'll look at your grades in the last 2 years when you apply to graduate school. It's like that. So the transgressions of one's youth can be ignored. They're forgiven. All right. So you just want to see the eventual behavior. The number associated with few is not specified. But that's a little relaxation of the criteria. Now, how to use this theorem? Well, first you have to show that the sequence is monotonically increasing or monotonically decreasing. In other words, you have to show that the next term is greater than equal to the previous term, or that the next term is less than or equal to the previous term. And this requires, of course, some algebra, and it may even require the proof by induction. We'll start off by trying to use algebra, right, and try to rewrite the expression. So set up the expression a to the n plus 1 is greater than or equal to a to the n, and put a question mark over that. Then try to rearrange the terms so that you get a to the n on one side and cancel it out. Anyway, leave a comparison with the number 1. That's easier to see. And here's an example. Let's look at the sequence. The sequence a to the n is 1 over n 5 to the n power. Obviously you know where this is going, but we want to use it as an example. The sequence is strictly decreasing since the next term, this would be, where's my pen? So what we're going to set up here is we're going to say is a to the n plus 1 is it less than or equal to, and I'll put a question mark over it because we don't know it right now, a to the n. So here is your a to the n plus 1, and here on this side is a to the n. Like I said, try to rearrange this. If I factor out 1 over 5, I would have 1 over 5 times 1 over 5 to the n, and then on the right-hand side, I still have 1 over 5 to the n, which can be canceled. So I end up with 1/5 is less than 1. Okay, that's true. You see, that's what happened, and that's great. Now, so this is a strictly decreasing sequence. All right. Now the largest term here is the first term, 1 over 5, because it's strictly decreasing. Actually, this is the least upper bound, but this is a decreasing sequence, so it's not going to converge to its least upper bound. But look at, all the terms are non-negative. Therefore, they're bounded from below by 0. In fact, 0 can show is the greatest lower bound. By the theorem, the sequence converges. You have a non-increasing sequence. It has a lower bound, the greatest lower bound of 0. It's going to converge to its greatest lower bound and converges, that is, to 0. This is just a second example of this theorem. Here we're going to use the sequence n times e raised to the minus n. Now this is strictly decreasing. We can set this up. Here we're going to look at, we're going to compare the next term to the previous term. So I just substitute in for n plus 1 and get the next term. I compare it to the term for n. Again, just do some algebraic rearrangement here. It doesn't take much. In other words, I factored an n out, then I have 1 plus 1 over n here. I end up with n e to the minus n times e to the minus 1. On this side I have n e to the minus n. You can cancel these terms right here, and end up with 1 plus 1 over n is strictly less than e. Is this true? Yes. Okay. So actually it does have a greatest upper bound. All the terms are non-negative. The greatest lower bound is 0. As before, this sequence converges to 0. I just wanted to point out that there is more than one way to test convergence. You know, just because you find one method doesn't mean there isn't another method. In fact, the other method might even be easier. For the sequence that we just did, which was n e to the minus n, we could have compared it to the corresponding real-valued function of x e to the minus x. Then we could have let x go to infinity, taking the limit as x goes to infinity of x over e to the x. Because I have an indeterminate form here, infinity over infinity, so I use L'Hopital's rule. 1 over e to the x, find that this sequence converges to 0, or the real-valued function converges to 0. Therefore, the sequence itself converges to 0. Also, I could have applied L'Hopital's rule without going to the real-valued function. So here were different ways to test the convergence for this sequence. 3 different ways, actually. There. They better all have the same answer. This is just an interesting result. Let's consider the sequence a to the n equals 1 plus x over n raised to the nth power. What I want to show you here is that you can have a real number in the middle of your sequence, but the sequence is still with respect to n. In this case, I'm going to just make some changes. I'll take the logarithm of both sides and end up with n times the natural log of 1 plus x over n. Again, x is just, it might as well be a constant here at this stage. Okay. Then I can try to take the limit, but I end up with an indeterminate form, so I applied L'Hopital's rule. But now what I want to point out here is that when you take these derivatives, take the derivative with respect to n, because x is just a constant. There's a tendency to take the derivative with respect to x, because we're so used to it. When we see an x, we take the derivative with respect to x. But in this case, the domain of the sequence is these natural numbers n. Right. We say here x is just a constant in this particular sequence. That's a particular value. So I can take the limit, and actually the limit is x. So the limit of the sequence is the value x that occurs in the statement of the terms of the sequence.